Assalamu alaikum. In today's lecture, we are going to cover the section 8.2 of chapter 8. Of course, we are doing the same chapter, advanced computing techniques. So, this is the title of the section, solving linear recurrence relations. So, as title says that we have to solve linear recurrence relations. So how to solve and how to find the solutions of linear recurrence relations and what are linear recurrence relations. Let's have a look at it. So this is the summary of the section, linear homogeneous recurrence relations. Then we learn to solve linear homogeneous recurrence relations with constant coefficients, and then solving linear non-homogeneous recurrence relations with constant coefficients. And the procedure is quite similar to the process of solving differential equations with constant coefficients, homogeneous and non-homogeneous. So let's see. First of all, there are a few definitions. A linear homogeneous recurrence relation of degree k with constant coefficient is a recurrence relation of this form: an is equal to c1 an minus 1 plus c2 an minus 2 plus so on ck an minus k, where c1, c2, ck are the real numbers, that is, they are constants, and ck is not equal to 0. So this is the linear homogeneous recurrence relation of degree k. Okay, so general form of the linear homogeneous recurrence relation of degree k is this. Now it is linear because the right hand side, that is this side of the expression, right hand side is the sum of previous terms of sequence each multiplied by a function of n. It is homogeneous because no term occur that are not multiple of these aj's, right? These are actually the terms of sequence. An is the nth term, and these are the preceding terms of the sequence. So the coefficients of the terms of the sequence are all constants. Ci's, that is, Ci's are all constants rather than the function that depends on n. Okay, next we used the degree. The degree is k because an is expressed in the terms of previous k terms of the sequence. That is why the degree of the recurrence relation is k. Okay, because an is expressed in the previous k terms in as a linear combination of the previous k terms. Okay. Uh, There are few examples. Pn is equal to 1.11 Pn minus 1. Here C is 1.11, that is the constant. Here is 1.11. Pn is the nth term and Pn minus 1 is the previous term. So this is a linear homogeneous recurrence relation of degree 1 because only one previous term is used to express this recurrence relation. Now, this is Fn is equal to Fn minus 1 plus Fn minus 2. So, this is linear, this is homogeneous. Of course, this is recurrence relation of degree 2 because two previous terms are used. Now, An is equal to An minus 1 plus An minus 2 squared. This is not linear because of this term, An minus 2 squared. So, this term is not linear. Now this relation hn is equal to 2hn minus 1 plus 1 is non-homogeneous because of this 1. Okay. Bn is equal to nbn minus 1 does not have constant coefficients because of this coefficient n. Right. So I hope you would have understood all the concepts. Now, solving linear homogeneous reconciliations. So, the basic approach is to look for the solution of the form an is equal to rn. So initially we are going to assume that an is equal to Rn, where R is any constant. Note that an is equal to Rn is the solution to the recurrence relation of this linear homogeneous uh, recurrence relation with constant coefficients of degree k, if and only if this Rn satisfies this relation, right? And when does this satisfy this relation? when we plug in this and the resulting relation is true. Okay, so let's plug in, because we are assuming that and we are claiming that this an is equal to Rn is the solution, so it should satisfy this relation, recurrence relation. So let's plug in the value. So we have Rn, because an is Rn, C1 as it is, an minus 1 is Rn minus 1, C2 as it is, an minus 2 is Rn minus 2, plus so on, Ck as it is, an minus k is Rn minus k. Now what is common here? Rn minus k is common. Okay, Rn minus k is common. So factor it out, and we have Rk minus C1 Rk minus 1 minus C2 Rk minus 2 minus so on minus Ck minus 1 R minus Ck is equal to 0. And this is obtained by factoring R minus K out and dividing by this. Okay, so we have this equation, and this is called characteristic equation. Now, the sequence an with an is equal to Rn is the solution of this recurrence relation if and only if R is the solution of this characteristic equation. Okay, so the solution to the characteristic equation are called the characteristic root of the recurrence relation. The roots are used to give an explicit formula for all the solutions of recurrence relation. So let's see how does it work. So first theorem, solving linear homogeneous recurrence relations of degree 2. So initially we are going to give a rule or give a formula for the recurrence relations of degree 2, then we'll generalize it. So let C1, C2 be the real numbers. Suppose that R squared minus C1R minus C2 is equal to 0 has two distinct roots R1 and R2. Okay, so what is important to note that roots are distinct, real distinct R1 and R2. Then sequence an is a solution of the recurrence relation an is equal to C1 an minus 1 plus C2 an minus 2 if and only if an is equal to alpha 1 R1n plus alpha 2 Rn2. Okay, for n is equal to 0, 1, 2, where alpha 1 and alpha 2 are constants. So if this is the characteristic equation for this recurrence relation, then its solution will be of this form, where R1 and R2 are distinct, which are roots of this characteristic equation. Okay, so an is equal to alpha 1 R1n plus alpha 2 R2n is the solution of this recurrence relation. All right. So let's apply this for to an example. What is the solution of this recurrence relation? An is equal to an minus 1 plus 2an minus 2. So this is linear recurrence relation. This is homogeneous recurrence relation, and its degree is 2 because the previous two terms are used. So its degree is 2. And initial conditions are given in order to find these alpha 1 and alpha 2. If initial conditions are given, we can find alpha 1 and alpha 2 because they are arbitrary constants. A naught is given equal to 2 and A1 is given as 7. So let's solve this. First of all, we need characteristic equation associated to this relation, and which is equal to r square minus C1 R. So C1 here is 1. So minus R minus C2, which is here 2. So minus 2 is equal to 0. So characteristic equation is R square minus R minus 2. But now we need to solve this in order to find the roots. So by solving, you can check the roots of this equation are r is equal to 2, r is equal to minus 1. That is distinct real roots. So according to the theorem 1, solution of this recurrence relation will be an is equal to alpha 1 2 to the power r1 to the power n, that is 2 to the power n plus alpha 2 r2 to the power n, so minus 1 to the power n. So this is the solution using theorem number 1. Now where alpha 1 alpha 2 are arbitrary constants, so in order to find the values of alpha 1 and alpha 2 we will use these conditions. a naught is equal to 2, that is replace n is equal to 0 here. When we plug in the value of n, we have a naught is equal to 2 to the power 0 is 1, so alpha 1 minus 1 to the power 0 is also 1, so we have alpha 1 plus alpha 2 is equal to 2 because a naught is equal to 2. So this is one of the equations. So a1 is equal to 7, that is 7 is equal to, now what we are going to do, we'll replace number 1, a1 in this an. So we have 2 alpha, when n is 1, this is 2 alpha 1 plus minus 1 into alpha 2. So we have these two equations. Now solving these two equations simultaneously, we have alpha 1 is equal to 3, alpha 2 is equal to minus 1. And so our solution is 3 into 2 to the power n minus 1 to the power n, right? So this is the solution and this is the application of theorem number 1. So there is another example. Use theorem number 1 to find an explicit formula for Fibonacci numbers, and the sequence Fibonacci numbers satisfies the recurrence relation Fn is equal to Fn minus 1 plus Fn minus 2 with the initial conditions F0 is 0 and F1 is 1. Okay. Now, so the roots of the characteristic equation. So first of all, characteristic equation. This is of degree 2. So C1, C2 both are 1. So R square minus R minus 1 is equal to 0. This is the characteristic equation. So roots are real distinct, and thus we have the solution. Fn is equal to alpha 1 r1n plus alpha 2 r2 to n, and so this is the solution of the recurrence relation. Now using the initial conditions, we have the values of alpha 1 and alpha 2. By plugging in the values of alpha 1 and alpha 2, we have this solution. Fn is equal to 1 over square root of 5, 1 plus square root of 5 divided by 2 to the power n minus 1 over square root of 5 into 1 minus square root of 5 over 2 to the power n. Okay. Now next, theorem number 2. Now when there is a repeated root, again we are talking about degree 2 recurrence relations, and roots of characteristic equations are repeated. Then what will be the solution? So let C1, C2 be the real numbers, which C2 is not equal to 0. Suppose that R square minus C1 R minus C2 is equal to 0. Has only one root R naught. A sequence an is a solution of the recurrence relation an is equal to C1 an minus 1 plus C2 an minus 2 if and only if an is equal to alpha 1 R naught n plus alpha 2 n R naught n. Okay, so n is multiplied in order to distinguish between the solutions of the recurrence relation. Okay. Now, there is one condition, C2 is not equal to 0. What if C2 is equal to 0? If C2 is equal to 0, then this is not degree 2 recurrence relation. So that is why the an minus k, coefficient of an minus k is not equal to 0, never be equal to 0. Otherwise, it is not going to be relation of degree k. Okay, so this is the reason for C2 not equal to 0. Okay, so let's apply this theorem. So we just have to remember these formulas. We are not going to prove this, and this is, as I told you earlier, it is quite similar to the construction of solution of differential equations which are linear and having constant coefficients and homogeneous as well. So the question here is, what is the solution of the recurrence relation an is equal to 6an minus 1 minus 9an minus 2, and previous two terms are used, therefore degree of this relation is 2, and this is linear, this is homogeneous, with the conditions a0 is 1 and a1 is 6. Now theorem number 2 will be used because we have this characteristic equation and it has repeated roots, that is r is equal to 3. So an is equal to alpha 1. According to this theorem, we just learned that alpha 1 r naught n plus alpha 2 n r naught n. Okay, so alpha 1 3 to the power n, because 3 is the value of r, and alpha 2 n into 3 to the power n. Now alpha 1, alpha 2 are constants to be determined, arbitrary constants, and we can determine by using these conditions. And so since a naught is 1, so a naught is 1 means alpha 1 plus alpha 2 is equal to 1. And so this is the first equation. But yes, alpha 1 plus alpha 2, it cannot be alpha 2 because n is equal to 0 will make this term 0 as well. So alpha 1 is equal to 1, right? So pardon me, I actually said alpha 1 plus alpha 2, but it is alpha 1 is equal to 1 because this term is going to be 0 when n is equal to 0. All right, so next a1 is equal to 6, that is replace n by 1, so we have this equation. Now from this we can find value of alpha 2 because alpha 1 is already obtained, which is 1. So alpha 2 is 1, and by plugging these values back to this solution, we have an is equal to 3 to n plus n 3 to n. Solving linear homogeneous equations, homogeneous recurrence relations of arbitrary degree. Now, if we have equation of arbitrary degree, that is of degree k, then the characteristic equation will look like this. And of course, this is a polynomial of degree k, so it must have k solutions. And if it has k distinct solutions, then our solution of recurrence relation is an is equal to c1 an minus 1 plus c2 an minus 2 plus ck an minus k. Is solution of this recurrence relation is given by alpha 1 r1n plus alpha 2 rn 2n plus alpha k rnk. Okay, so if we have a recurrence relation of degree k and its characteristic equation has distinct k roots alpha 1 alpha 2 up till alpha k, then the solution of this recurrence relation is given by this sequence, okay, where alpha 1 alpha 2 alpha k are constants and they can be determined if initial conditions are given. Find the solution to the recurrence relation. Now we have a relation of degree 3 and this is homogeneous and conditions are given. A0 is 2, A1 is 5 and A2 is 15. So in order to solve this we need characteristic equation, and characteristic equation is obtained by R3 minus C1 r square, that is minus 6 r square, minus C2 r, that is 11 r, and minus C3, that is minus 6. So this is the characteristic equation. This is equal to 0, of course. Okay, the characteristic polynomial is this. When we have a characteristic equation, we must put it equal to 0. So factorizing this characteristic polynomial, we have r minus 1 multiplied by r minus 2 multiplied by r minus 3. Now put it equal to 0, we have r is equal to 1, r is equal to 2, r is equal to 3. That is, we have three distinct roots of the characteristic equation. So solution of this recurrence relation will be an is equal to alpha 1 r1 1 n means 1 to the power n plus alpha 2 2 to the power n plus alpha 3 3 to the power n, right? Now in order to find the values of alpha 1 alpha 2 alpha 3 we'll use these three conditions and solve these equations simultaneously. We'll have alpha 1 is equal to 1, alpha 2 is equal to minus 1, alpha 3 is equal to 2, and finally the solution will become an is equal to 1 minus 2 to the power n plus 2 into 3 to the power n. The general case with repeated roots. So if we have a recurrence relation of degree k, which is linear, which is homogeneous, then the characteristic equation for this recurrence relation will be rk minus c1 rk minus 1 minus up till minus ck is equal to 0. And if it has repeated roots with multiplicity m1 m2 up till mt respectively, It has t repeated roots with multiplicity m1, m2, mt, where mi is greater or equal to 1. Then the solution of this recurrence relation will be of this form. Uh, R1 is of multiplicity M1, right? So you just need to understand the idea. R1, the root R1 is of multiplicity M1, okay? So how will we write the expression for R1? Alpha 1 0 plus alpha 1 1 n, okay? Alpha 1, that is the first root, coefficients of first roots are denoted by alpha 1s, alpha 1 j's, alpha 1 0 plus alpha 1 1 n plus alpha 1 2 n square up till alpha 1 m 1 minus 1 n to the power m, this is I guess L, it should be 1, 0 1 2 and up till L, I guess up till L, right? So this is M1 minus 1, right? This is no L. Let me read it again. Alpha 1 0, alpha 1 1 into n plus up to alpha 1 M1 M sub 1. This is M sub 1. Okay. This is this M1. M sub 1. M sub 1 minus 1. N to the power M sub 1 minus 1. Right? Into R1 to the power n. Similarly, R2 has multiplicity 2. That is R2 is repeated M2 times. R2 has multiplicity M2. That is R2 is repeated M2 times. So, plus alpha 2 0. That is we are talking about R2. Alpha 2 0. Alpha 2 1 into n plus so on. Alpha 2 m2 minus 1, m sub 2, this is m sub 2 minus 1, whatever the value of m sub 2, that is the multiplicity, minus 1, 1 less than m sub 2, this means n to the power m sub 2 minus 1, okay, multiplied by r2 to the power n. And similarly, continuing this way, rt, the root rt is of multiplicity mt, okay. So alpha t0 plus alpha t1 n plus up till next term will be alpha t2 n square and so on alpha t mt. Mt is this multiplicity m sub t minus 1, that is 1 less than this multiplicity. If mt is 3, then it should be 2, okay. N to the power mt minus 1 rt to the power n, where n range to 0, 1, 2, so on, where alpha I, j are the constants for I less or equal to t and greater or equal to 1, that is I lies between 1 and t, and j lies between 0 to mi minus 1, that is 1 less than mi, okay. So I hope now this notation is clear. So how to use this? Let's find out through an example. Question here is find the solution of the recurrence relation an is equal to 3 minus 3an minus 1 minus 3an minus 2 minus an minus 3. So this is the degree 3 recurrence relation, and conditions given are a0 is equal to 1, a1 is equal to minus 2, a2 is equal to minus 1. So the first of all we have to find the characteristic equation. A characteristic equation is given by this equation: r cube plus 3r square plus 3r plus 1 is equal to 0. And because all the c's are minus 1, so that is negative, so that is why you can see all the positive terms here. So this is nothing but r plus 1 cube, and we have r is equal to minus 1 is the root of this characteristic equation of multiplicity 3. Okay, so we have only one root. and it is of multiplicity 3. Okay, so what we are going to do, so an is equal to alpha 1 0 minus 1, r is minus 1 to the power n plus alpha 1 1 n minus 1 to the power n, okay, plus alpha 1 2 n square into minus 1 to the power n. So multiplicity 3, so we ended up n to the power 3 minus 1, right? So that was the m1 minus 1 and m2 minus 1 and mt minus 1. So this is how it works. So we ended up with 3 minus 1, that is n square. Okay. Now to find the constants, procedure is same. We'll just plug in the values and use the conditions, and then solve simultaneously, and we'll have the values of alpha 1 0, which is 1, alpha 1 1, which is 3, alpha 1 2, which is minus 2. An is equal to, by plugging in back, plugging in all the values back to the solution, we have the solution 1 plus 3n minus 2n square into minus 1 to the power n, because minus 1 to the power n is common. That is actually r to the power n, right? Next, linear non-homogeneous reconciliation. So far we have discussed the different cases for homogeneous reconciliations. Now, what if we have a non-homogeneous linear reconciliation with constant coefficient? Then how to solve this? First of all, let's define it. A linear non-homogeneous reconciliation with constant coefficient is a reconciliation of the form an is equal to c1 plus an minus 1 plus c2 an minus 2 plus so on ck an minus k plus fn. Now this fn actually makes it non-homogeneous, where c1, c2, ck are real numbers and fn is a function not identically 0 depending only on n. Okay, the recurrence relation is called the associated homogeneous reconciliation. Again, the concept is quite similar to the concept in differential equation. So this is called associated homogeneous reconciliation. And in order to solve this non-homogeneous reconciliation, we have to solve the associated homogeneous reconciliation, and then we'll find a particular solution for this non-homogeneous relation, and then we'll add them up to find the general solution of the reconciliation. So there are a few examples. An is equal to an minus 1 plus 2 to the power n. This is a non-homogeneous linear reconciliation. Because of this term, this is non-homogeneous. This is also a non-homogeneous linear reconciliation. This is also non-homogeneous linear reconciliation with constant coefficients as well. And this is also a non-homogeneous reconciliation. Because of this, this is non-homogeneous, and this is linear. This is with constant coefficients, and these are the homogeneous. Associated homogeneous reconciliations of all these relations respectively. Okay, so associated homogeneous of this is this, of this is this, third one is this, third one, and fourth one is this, fourth one. Okay. Now, theorem number 5, how to solve non-homogeneous linear reconciliations with constant coefficients. So, as I said earlier, we have to solve in two parts. In step 1, we'll solve the associated homogeneous linear reconciliation, and in step 2, we'll find the particular solution for the non-homogeneous one, and then we'll add both the solutions to find the solution. Now, if A and P is a particular solution of a non-homogeneous linear recurrence relation with constant coefficients, this is the reconciliation, then every solution of the form A and P, that is the particular solution, plus A and H, that is the solution for associated homogeneous equation, homogeneous reconciliation, which is given by this. This is the associated homogeneous. So the general solution will be A and P plus A and H. Okay, A and P is the particular solution, A and H the solution of associated homogeneous recurrence solution. Okay, let's solve a problem to have deeper insight of the method. So find all the solutions of reconciliation. A n is equal to 3 into A n minus 1 plus 2n. Now we'll use the method of undetermined coefficient type method, which you would have learnt in differential equations. What is the solution with A1 is equal to 3? So first of all, we have to find the solution of associated homogeneous reconciliation, and homogeneous reconciliation is a n is equal to 3 a n minus 1. So characteristic equation associated to this is r minus 3 equal to 0, so r is equal to 3. So solution of this reconciliation, this is a reconciliation of degree 1, so a solution of this reconciliation is equal to a n is equal to alpha 3 to the power n, and this h indicates the solution of associated homogeneous equation. So this is the solution of associated homogeneous equation. Now fn is equal to, since fn is equal to 2, so we'll assume uh, uh, a solution of this non-homogeneous equation, and we'll assume of the same type. Okay, so fn is a polynomial, so we'll assume a polynomial solution. Fn is equal to 2n. This is a polynomial of degree 1. Okay, what is the general form of degree 1? General form of degree 1 is an plus b type, cn plus d type. Okay, so general form, if we have a polynomial, then we will assume a solution of same polynomial of same degree in general form. Okay, so if we have fn is equal to 2n, this is a linear polynomial. So we are going to assume that the linear function like Pn is equal to Cn plus D is the solution of this equation. So this is our assumption. Now C and D are unknowns, so we have to find C values of C and D for which this Cn plus D is the solution of this reconciliation. Okay, so this is the procedure. Now, as we claimed that Pn is equal to Cn plus D is the solution of this, so it should satisfy this equation. So just plug it in this equation. So we have an, that is Pn. Pn means an is equal to Pn. Pn is the solution. That is, when we replace an by Pn, then this equation must be satisfied. So it should be actually A and P of this type, right? Uh, so by plugging in this equation, we have uh, Cn plus D is equal to 3 Cn minus 1 plus D, because An is Cn plus D, so An minus 1 must be Cn minus 1 plus D, right? So our equation becomes Cn plus D, 3 into Cn minus 1 plus D plus 2n as it is. Okay, so we have assumed that the solution of this is of this form, and then we plugged it in the original equation, and we have consequently this equation. Now, in order to find values of C and D, we have to compare the coefficients, right? So you can see 2 plus 2Cn plus, this can be rearranged as 2 plus 2Cn plus 2D minus 3C is equal to 0. Now since this is polynomial, right side is also polynomial, so both the sides are equal if the coefficients of corresponding terms are equal. That is 2 plus 2C must be equal to 0 and 2D minus 3C must be equal to 0. So by solving these two equations, we have C is equal to minus 1, D is equal to minus 3 by 2. Now by backward substitution, so our assumption was Cn plus D is the solution of this. So C is minus 1, D is minus 3 by 2. So minus b minus 3 by 2. So our a and b, that is our particular solution, is minus n minus 3 by 2. Now the general solution is a and b plus a and h. Okay, so we just plug these values into this. So minus n minus 3 by 2 plus alpha 3n, where alpha is a constant, and this constant can be determined by this initial condition. Okay, so a1 is equal to 3 gives us 3 is equal to minus 1 minus 3 by 2 plus alpha. So this gives us the value of alpha, and which is equal to 11 by 6. Okay, so put this value of alpha in this an. So we have the solution. Finally, we have the solution of this reconciliation, given reconciliation. An is equal to minus n minus 3 by 2 plus 11 over 6 3 to the power n. Now another example of non-homogeneous reconciliation. Now this non-homogeneous reconciliation is of degree 2, and this 7 to the power n makes it non-homogeneous. So first of all, first step of the solution is to find the solution of associated homogeneous reconciliation. So associated homogeneous reconciliation is an is equal to 5an minus 1 plus 6an minus 2. So now you, I hope you have learned how to find the solution. So you will find the characteristic equation, and then by solving it to find the roots of the characteristic equation and the solution of homogeneous reconciliation depends upon the roots, and roots are 3 and 2. You can verify it yourself. So homogeneous associated homogeneous solution is alpha 1 3 to the power n plus alpha 2 2 to the power n, where alpha 1 alpha 2 are constants, and Fn is 7 to the power n. So since this is of the type 7 to the power n, so we'll assume that our a and b is of the form c into 7 to the power n, where c is the constant. So our assumption depends upon the type of Fn actually. Now c is the constant to be determined, and we'll determine it by substituting this c into f to the power 7 to the power n into the original equation. So by plugging this into the recurrence relation, left hand side is c into 7 to the power n is equal to 5, right hand side is 5 a n minus 1. Since a n is c is 7 to the power n, then a n minus 1 is c 7 to the power n minus 1. So 5c 7 to the power n minus 1, and so on, minus 6c 7 to the power n minus 2 plus 7 to the power 1 n as it is. Okay, so what is common actually factor which we can factor out? Factoring out 7n minus 2 is common. So factoring out 7n minus 2, this equation becomes 7 square, that is 49c. This is equal to 7 into 5, that is 35c, minus 6c, because 7n minus 2 is factored out, and plus 7 square, that is 49. Okay, so from this we have 20c is equal to 49, that is c is equal to 49 divided by 20. So a and b is equal to 49 divided by 20 into 7 to the power n. So the general solution is a and h plus a and b, and which is equal to alpha 1 3 to the power n plus alpha 2 to the power n plus 49 over 20 7 to the power n. Okay, I hope this method is not difficult. So let's practice few questions from the exercise. Let's start with the easier one. Solve this. This is what is this? I think this is the part C of question number 3 of the book, if I'm not wrong. An is equal to 5 an minus 1 plus 6 an minus 2. This is homogeneous linear reconciliation with constant coefficients, and its degree is 2, and the initial conditions are a naught is equal to 1, a1 is equal to 1. So corresponding characteristic equation will become r square minus 5r plus 6 equal to 0, and its factors are r minus 2 into r minus 3 is equal to 0. So r is equal to 2, r is equal to 2. That is, it has distinct characteristic equation has distinct real roots. So using theorem number 1, solution will be alpha 1 2 to the power n plus alpha 2 3 to the power n. Now, in order to find the values of alpha 1 and alpha 2, we have initial conditions. And using these conditions, we have the value of alpha 1 is equal to 0, and the value of alpha 1 is equal to 3, and the value of alpha 2 is equal to minus 2. So a n becomes 3 into 2 to the power n minus 2 into 3 to the power n. Question number 13. Find the solution to an is equal to 7an minus 2 plus 6an minus 3 with a naught is equal to 9, a1 is 10, a2 is 32. Okay, and this is again homogeneous reconciliation of degree 3 with constant coefficients, and you can solve this by solving this uh, characteristic equation. Corresponding characteristic equation is r cube minus 7r minus 6 is equal to 0, and in order to find the roots, we will start with the guess method. So whenever we have a cubic polynomial, we start with the by checking that minus 1 1 minus 2 2. If one of the integers is the root, then we can find rest of the roots by the quadratic factor of the equation, right? So minus 1 satisfies it. So if minus 1 is the root, then r plus 1 is the factor. So in order to find the second factor, we can divide this by r plus 1. So we have the second factor, r square minus r minus 6. So one of the roots is r is equal to minus 1. In order to find other roots, we have to solve r square minus r minus 6 is equal to 0. So we have three roots, minus 1, 3 and minus 2. By solving this quadratic part, we have the roots r2 is equal to 3 and minus 2. So we have three distinct real roots. So a n is equal to alpha 1 minus 1 to the power n plus alpha 2 3 to the power n plus alpha 3 minus 2 to the power n. Now, in order to find the values of alpha 1, alpha 2, alpha 3, we have to use these initial conditions, and you can find the values, and these values are given by alpha 1 is 8, alpha 3 is minus 3, alpha 2 is 4. So we just plugged in the values in order to find the solution. Okay. Now, next question. What is the general form of the solution of the linear homogeneous reconciliation if its characteristic equation has roots 1, 1, 1, that is 1 of multiplicity 4, minus 2 is the of multiplicity 3, and 3 is of multiplicity 2, and minus 4 is a single root. Okay, so according to theorem 4, we have R1 with multiplicity 4, R2 minus 2 which is multiplicity 3, and so on. I just have told you. So our general solution becomes looks like this. Okay, so alpha 1 0 plus alpha 1 1 n plus alpha 1 2 n square plus alpha 1 3 n cube. Because multiplicity is 4, so we ended up at 4 minus 1, that is n cube, right, into 1 to the power n, r1 to the power n. Okay, similarly multiplicity 3, so we will end up with n square. Okay, and so on, right. I hope this is clear now. Now there is a question 29. Find all the solutions of the recurrence relation an plus 2an minus 1 plus 3 to the power n. Now this is non-homogeneous, and this 3 to the power n make it non-homogeneous. So first of all, we have to find the solution of associated homogeneous recurrence relation, which is an is equal to 2an minus 1, and the a and h is equal to alpha 2 to the power n. Okay, now in order to find a and b, we have to assume that c into 3 to the power n is a and b, because our fn is 3 to the power n, so we'll assume the same type of the solution, that is c to the power c into 3 to the power n, and then the same procedure we'll plug in A and P into this equation in order to find the value C. So C is 3. So by plugging in back, A and P is equal to 3 into 3 to the power n, so which is equal to 3 to the power n minus 1. So the general solution is A and H plus A and P. So alpha 2 to the power n plus 3n plus 1. Okay. So this is the general solution. In part B, initial condition is given, and this condition will be used to find the value of alpha. Okay. So you can do it yourself. And that is all for today. I hope you would have learned something new, and this is not that difficult actually. A bit of practice is required. Okay, good luck. Take care.